In the last video, we covered the physical properties of color, mass, weight, and volume. If you haven't already, you can watch this video on the channel as well. This video will cover part 2 of the physical properties of matter. Let's begin with density. Density is how tightly matter is packed together in something. It's actually a combination of the concepts of mass and volume, since mass is the amount of matter in something and volume is the amount of space something takes up. Density actually refers to the amount of matter in a given space. So how tightly those atoms are close together. An example that we're going to use to understand density better is a golf ball versus a ping pong ball. I think you will agree that ping pong balls and golf balls roughly have a similar volume. They take up about the same amount of space. However, I think you will also agree that they have a very different mass and also a very different density. We understand that a ping pong ball is hollow with a lot of air inside, while a golf ball is very dense. So their masses are going to differ because the golf ball has a greater density. It has much more stuff tightly packed together in a very similar amount of space to the ping pong ball. So density actually has a mathematical formula. For your knowledge, I wanted you to know that if you have the mass of an object and you also found the volume of an object, you can divide those two measurements and arrive at the object's density. And therefore, density is a fixed property of elements in our world. For instance, the element mercury, which is harmful to people, so we should never touch or interact with it. It actually has a fixed density of 13.6 grams per centimeters cubed. So if I ever found, say, a unknown silver metal on a lab table and I were able to identify its mass and its volume, then I could find its density. And if it were 13.6, I should be very nervous because I'm dealing with some mercury. On the other hand, let's look at another similar silver metal called platinum. Platinum has a density of 21.5, which is more dense, clearly platinum. No wonder jewelry is often made out of platinum because we wouldn't want things like rings to break. And platinum is very durable. It's very, very hard to break because its density is so high. Finally, let's look at the last example of a silver metal in aluminum. Take a guess as to the density of aluminum, and I want you to think about the same aluminum that is found in the aluminum foil that you might wrap your lunch sandwich in. You're right, it has a density of 2.7 grams per centimeters cubed, a lot less than platinum and mercury. And we know that through experience because aluminum foil is very, very malleable. It's easy to rip up because those atoms are not tightly packed together at all. Finally, here is a chart that summarizes the basic densities of popular types of matter in our world. Take a look at air. Air's density is 0.0013, meaning air is not dense at all. Air is a collection of different gases and elements, and those atoms are very, very far apart, which is why it's very easy for us to move through air as opposed to water and as opposed to solid objects like my lab table. Density also has an effect on whether objects float or sink. So if we take a look at wood, for example, oak wood, on average it might have a density of 0.85, which is why sometimes we can see things like wood floating in water, which has a density of 1. This whole density chart was created around water, which is why water's density is always 1 grams per milliliter. And anything that has a lesser density, such as wood or ice, will float on the more denser object. And now finally, I just want to talk about the phenomenon of ice and water. It is true that gases tend to be less dense than liquids, and liquids tend to be less dense than most solids, such as gold. Look at gold, 19.3, water only 1. However, water is the only exception to this rule because when liquid water freezes into solid ice, something very special happens to the molecules that we can't see. They form hydrogen bonds, which are very, very organized combinations of H2O molecules. What I mean by that is the solid form of water actually is more organized than the liquid form, making it less dense than the liquid form, making ice able to float on liquid water. Its solid form is actually less dense than its liquid form. But in other instances, if I were to have solid aluminum and liquid aluminum would definitely be less dense than solid aluminum, meaning that a solid chunk of aluminum would sink right to the bottom of a glass of liquid aluminum. This is true for everything else except water. Finally, here's an illustration. Which is usually most dense, solids, liquids, or gases. Once more, we can visibly see that solids are more dense because the atoms are tightly packed together, as opposed to liquids, and then look at gases where they're very far apart. Again, the one exception is water. And here's a beautiful glass of water and ice floating. Number 5, temperature. Temperature is defined as how fast the atoms of a substance are moving. So it's actually about the speed of atoms. And you can guess that if the atoms are moving faster, the temperature will be hotter, and if the atoms are moving slower, the temperature will be lower. There are two concepts of temperature that I'd like you to know. The first is melting point. Melting point is the temperature at which a substance changes from a solid to liquid. It can also be looked at as the freezing point, the point when a liquid goes to a solid form. But in terms of melting point, in the metric system, we follow centigrade or Celsius as our unit, and the melting point of water is exactly 0 degrees Celsius because this whole Celsius system, the centigrade system, was created on the basis of water. On the other hand, boiling point is the temperature at which a substance changes from a liquid to a gas. And once again, this whole system was created around water, so the boiling point of water is going to be a nice and easy number at 100 degrees Celsius. And in Fahrenheit, it's not an easy conversion, but there is a formula you can use to convert to Fahrenheit. The numbers are not as nice, but we're going to stick with Celsius since in science class we focus on using the metric system. Okay, here is a thermometer. Back in the day, thermometers used to be made out of mercury, as many of you know, but recall that mercury is a silver metal. So if your thermometer at home has a red fluid in it, that is red food coloring mixed in an alcohol base. It is not mercury, so you do not have to fear. Thermometers in America will have both Celsius and Fahrenheit, hopefully, so we can see both systems at work and you can visually compare the difference between temperatures. For instance, scientists say that room temperature is about 22 degrees Celsius, as we can see on this thermometer, and that's a little above 70 degrees, so around 72 degrees in Fahrenheit. And if you're wondering why there are two tens, it's because anything below 0 are referring to negative degrees. Physical property number 6 is conductivity. Conductivity refers to how fast electricity or heat can be transferred through a substance. All metals are good conductors of electricity and heat, which is why copper wires largely make up our electronics, like the charger that is connected to your laptop. Although on the outside we can't see any copper wires, if we were to cut open the plastic, rubber, silicone casing, it would all internally be made up of copper because metals are very good at transferring heat and electricity. And if we want power to be transferred to our laptop to charge it quickly, we're going to use metal. Also, this explains why a lot of cookware is made out of metal as well, because they're very good at transferring and also retaining heat. The antonym of a conductor is what we call an insulator. So nonmetals are insulators because they're poor conductors of electricity and heat. And that's a great thing because, for example, we're able to hold very hot things in materials such as styrofoam, rubber, that would not burn our hands and be able to insulate instead of conduct heat. so they can protect us. But be mindful that styrofoam is a man-made material that is not able to be recycled, so we don't want to use a lot of it. And notice that the copper wires of your electrical wires that run through maybe your laptop charger may be covered in plastic or rubber to protect us from conducting any heat or electricity ourselves. And finally, air is actually an excellent insulator. Our hydro flasks, our swell bottles, a lot of these metal thermoses that carry soup and keep it warm for long hours, it's double wall insulated, meaning there's an internal layer of metal that can get very hot, but then the manufacturers left a space for air, and then the outside that we actually touch is a second layer of metal, meaning that that air is insulating the hot heat from the soup or water or drink that you've put in your thermos. Therefore, we are not able to feel the heat that is actually inside because of that double layer and the air protecting us. Here's a picture of some nails conducting heat. Since they're made out of metals, they're very good at conducting and retaining that heat. Here's an example of styrofoam. We're on to our last physical property, physical state. Matter can exist actually in 4 states or phases. You may be most familiar with the first 3. Matter can exist as a solid, as a liquid, as a gas, and actually also as plasma. And we'll talk more about plasma soon. The 3 main states of matter that exist on Earth are solids, liquids, and gases, and they are the first we're going to talk about. The solids are the groups of matter that have atoms that are packed tightly together and have low kinetic energy. Kinetic energy is the energy of movement, so it means that the atoms in a solid are not moving very fast. They're moving very slowly and vibrating very, very subtly. But in liquids, the atoms are close, but not as close as solids, and they actually flow around each other and have more kinetic energy than in solids. And you're probably seeing the trend. Gases, atoms are very far apart and are moving fast with high kinetic energy. Solids have a definite shape, while liquids do not have a definite shape. What this means is liquids usually take the shape of whatever container they are in, and this is true for gases as well. Solids have a definite volume or amount of space they take up, and liquids do too, because for instance, a 100 milliliter water bottle, which is very small, let's go with a 1,000 milliliter water bottle, can only hold 1,000 milliliters. But gases differ because they do not have a definite volume, and they will take up whatever space you offer them, although the amount of pressure may increase if you give them a smaller space. Some examples of solids include wood, chair, jello. Liquids include water and milk, and for gases, air. Here's a picture of a potato chip bag in an airplane. It has a lot of air in it because as we increase elevation, the amount of pressure decreases. So if there's less pressure, gases are going to spread out because those atoms like to spread out from each other. And if there's less pressure, they are going to spread out in however much space you give them. So next time you take a plane ride, feel free to take a bag of chips and see it kind of puff up like this. It's a cool phenomenon. The last physical state of matter is number 4, plasma. Plasma may be a new concept to some because it is not a common state of matter on Earth. Instead, it's very, very common in space, in outer space. Plasma is made of highly charged atoms with extremely high kinetic energy. So think about the state of matter of gas, but electrically charged. Some examples of plasma might be stars, like the sun, neon signs, and flames. Here is beautiful sun, some flames, and a neon sign. And this is the aurora borealis, also another phenomenon we see on Earth and an example of plasma. And that's it for this video, but you can continue watching and learning about the chemical properties of matter in part 3 of this lesson. The link to part 3 can be found in the description box below.